Plant a single Norway spruce, and it grows at an exceptional rate, producing a dense evergreen canopy that permanently starves surrounding flora of sunlight. In the 1930s, the Italian government recognized this biological efficiency and launched a massive initiative across the Prealps region near Lake Como to blanket the terrain in Norway spruce. This was a highly orchestrated operation executed by a specific state military apparatus, the Militia Forestale. The economic rationale was entirely focused on yield. Italy faced a soaring national demand for timber, and the mandate explicitly required planting fast-growing monocultures to secure a reliable, high-volume supply. To meet those targets, the government eradicated centuries-old natural pastures and deciduous meadows, replacing them with artificially uniform spruce grids. Ecological consequences were entirely excluded from the calculation. That 1930s mandate established an operational baseline that still governs commercial forestry and global carbon offset programs today. Prioritize rapid, single-species growth above all other metrics. We can now evaluate the physical results of that decision. 9 decades have passed, giving the Italian plantations ample time to settle into mature forest ecosystems. But the physical reality beneath the canopy reveals a stagnant environment. Plant diversity in these mature spruce grids remains 50.3% lower than in the neighboring native deciduous forests. Researchers quantify this failure using functional evenness, a measure of how efficiently a plant community uses available ecological space. The Italian spruce system operates at a 30%. Despite generating ecological dead zones, monocultures composed of spruce, eucalyptus, and pine are still regarded by the industry as the absolute best mechanism to optimize rapid carbon sequestration. A 2023 global meta-analysis demonstrates that this core assumption is statistically false. Mixed-species forests actually overyield monocultures in total carbon storage. The failure of the Italian monoculture starts at the canopy level. Because the spruce is an evergreen, it permanently blocks the spring light window. Native deciduous trees drop their leaves in winter, allowing a critical burst of spring sun to reach the forest floor. The spruce's permanent shadow eradicates the early blooming understory plants that rely on that seasonal light. The damage continues underground. Spruce needles decompose at an incredibly slow rate, causing them to accumulate massively on the surface over decades. This thick, stagnant litter layer actively alters the chemistry of the soil beneath it. The first measurable shift is a severe spike in the carbon-to-nitrogen ratio within the soil profile as the undecayed matter builds up. This initiates a secondary shift. The high acidity from the needles mobilizes exchangeable aluminum in the soil, which acts directly as a suppressant to new plant growth. The spruce acts as an agent of pedological decay. By engineering a hostile, highly acidic environment, it severely restricts the total biomass the plot of land can support. The 2023 global meta-analysis by Warner et al. Provides the statistical counterargument to the Italian failure, utilizing data from 79 distinct mixed to monoculture comparisons. This forest plot charts the standardized mean difference, a metric used to compare above-ground carbon stocks across different types of forest planting treatments. The first baseline finding reveals that mixed planted forests store roughly 70% more above-ground carbon than the average monoculture. Against optimized commercial timber species, the gap remains. Mixed forests hold 77% more carbon than single-species plots specifically engineered for high yield. This data establishes a phenomenon known as transgressive overyielding, the biological capacity of a diverse plant system to outcompete the absolute highest performing single species within that same group. There is no carbon penalty for introducing variety. In fact, mixtures frequently yield a net gain of 127.
A 4-species mix comprising Betula, Fagus, Quercus, and Tilia generated a quantitative yield of 43.9 megagrams of carbon per hectare. The monoculture average produced just 6.5. It's commonly assumed that specific biological traits, such as incorporating a nitrogen-fixing tree or relying strictly on native origins, are responsible for driving this boost, but the data confirms they are not. The mechanism driving the yield is spatial niche complementarity. Different tree crowns naturally grow into unique spaces, maximizing total solar capture without directly competing for the exact same block of sunlight. Spatial efficiency, how distinct crown architectures physically interlock to share a canopy, dictates carbon overyielding far more than isolated soil additives or specific functional tree types. Forest dynamics naturally shift over decades. The biological advantages of diverse plantations are not static. They fluctuate as the canopy matures. These charts modeled the relationship between stand age and overyielding compared to monocultures. Following the curves, diversification effects accelerate rapidly during early stages. The yield advantage reaches its apex at exactly 17 years post-planting, before canopy competition tightens. While data is currently limited for forests older than 28 years, this 17-year optimization peak perfectly aligns with the urgent, medium-term timelines demanded by international climate action goals. We can apply these biological realities directly to international forest restoration pledges. Currently, 45% of global land committed to ecological restoration is slated for commercial monoculture plantations. We evaluate these protocols across 3 critical vectors: carbon yield, soil toxicity, and functional evenness. On every metric, a monoculture model pioneered in the 1930s actively limits and damages modern global carbon offset potential. Abandoning the single-species approach for a 3 to 4 species planting protocol is no longer an ecological preference. It is a strict mathematical requirement to maximize total carbon yield and guarantees structural resilience for the decades ahead.
Scientists are racing to unlock technologies. Breakthroughs in AI are reshaping our future. The future is arriving faster than expected.